Well, good afternoon to all of you. Well, let us just continue from where we were about a week ago. You may recall that we're still in Chapter 7 and we're dealing with entropy. We know that we have equations which would allow us to find the entropy change for such things as ideal gases. We also know that we can simply find entropy for pure substances like water or R134a just by going into the tables. But if we have either solids or liquids or ideal gases, then we're going to have to use equations in order to find the entropy change. And this is consistent with our previous work when we were looking at finding internal energy or enthalpy changes for solids, liquids, or ideal gases. We used equations, and these equations are always a function of specific heats, or in the case of solids and liquids, we can call that the heat capacity. So we're doing much the same now. Now, we've already looked at the general equations. I've given you one example actually two examples, one for a closed, one for an open system, where we see how to find the entropy change for these types of systems. But now we want to look at the special case. You may recall that we've talked about not just finding an entropy change, but noting that the entropy change would be zero if we had an internally reversible adiabatic process. So that's what we're going to do now. We're going to look at an internally reversible adiabatic process, specifically for an ideal gas. Now let's note that when it says internally reversible adiabatic, then that also means what? It means that it's isentropic. So in other words, for this particular case, S1 is going to equal S2. So what I'd like to do is I want to go back to one of those relationships that was developed last time. It's basically the one that said S2 minus S1 is equal to CV times the natural log of the temperature ratio, and then plus R times the natural log of the specific volume ratio. Okay. So we're going to start with this particular equation. Let me again remind you that in the context of this problem, 1 and 2 could either represent the initial and final state for a closed system, or it could represent the inlet and the exit state for a single stream steady flow system. The equations are identical. So if indeed we're talking about an internally reversible adiabatic process, it's also isentropic. In other words, the entropy change is zero. So therefore, this equals zero, right? S2 equals S1, so this equals to zero. So let's just rearrange. So the natural log of T2 over T1 is going to equal minus R over CV times the natural log of V2 over V1. And then what I want to do is I just want you all to recall that when you have logarithms, if you have something in the form a log x, that's the same as log of x raised to the 8th power. So this is the same as the natural log of V2 over V1 raised to the minus R over CV power. What I can do at this point is I could also note that we could simply invert the V2 over V1 in order to get rid of the minus sign. Even the minus sign just means inverse. So this is equal to the natural log of V1 over V2 to the R over CV power. I further want to note that since we now have the natural log on both sides, I can just raise both sides above E. The E and the natural log cancel. So we get T2 over T1 equals V1 over V2 to the R over CV power. However, one might also note that R is equal to the difference between CP and CV. Now, this is not something I derived for you, but it was something that I had mentioned when we were first talking about specific heats. I had mentioned that, not only did R equal CP over CV, that we also have something called K, which is the ratio of specific heats, which is CP over CV. So since R does equal CP over CV, this is now V1 over V2 raised to the Cp minus Cv over Cv. Or to put it in its final form, the temperature ratio equals that volume ratio. And let's see, Cp over Cv is equal to K, right? So also K equals Cp over Cv. So therefore, this would be K minus 1. And this is one of the relationships that we would utilize if we have a isentropic process, that is an adiabatic reversible process specifically for an ideal gas. Now, this should make sense to you, right? If we look at some of our previous example problems, if we have a pure substance, then we would actually use our property tables. But here we don't have property tables, right? We're using temperature data within our equations, and this is the result of the equation. So if we have an isentropic process, then this particular relationship will hold. I'll give you an example problem here shortly so that we know how to use these. Now, this is only one equation. There are certainly other equations that one could use. So, for instance, what if I started with the other example, the other equation, the one that said that the entropy change equals Cp times the log of the temperature ratio minus R natural log pressure ratio. I can start with that particular equation. And I could go through, some similar derivations. This is still going to equal 0. I don't want to have to go through the mathematics, but the mathematics is actually very similar to the mathematics above. If we plug PV equals RT into the above and manipulate. And again, I'll just let you guys who feel so inclined to do this on your own. But what we would find is the following. We'd find that the temperature ratio T2 over T1 is going to equal the pressure ratio P2 over P1 raised to the K minus 1 over K power. So, clearly I've skipped a lot of steps between that statement and this result, but it's not a difficult derivation. It's very similar to the one above, and again, I'll just let you guys go through it on your own. One might also note that if we plug the ideal gas equation into this equation, for instance, I can apply this at both point 2 and point 1, the R's are going to cancel, and you're going to end up with temperature ratio and volume ratio terms. And further, we would find that this temperature ratio is going to equal V1 over V2 to the K minus 1, which is exactly the same as we had above, which is what I would expect, right? Just because we're potentially using a different equation doesn't mean we should get different results. So we have found through this other equation essentially the same thing. So ultimately, let's put a big giant box around it. This equation is the equation that we're going to use for an isentropic process involving an ideal gas. Okay. Now, yes? Yeah, this just has to do with the negative sign and the exponent up here. Let's say we had x to the minus 1, that's the same as 1 over x, right? If we have any variable to a negative power, it's the same as 1 over that variable. So basically, I've just said that this is now 1 over V1 over V2. 1 over V2 over V1, which is V1 over V2. So yeah, it's just a mathematical manipulation. The minus sign causes the specific volume terms to invert. Okay. All right. So let me just go through an example problem. And this example is actually not in your book, so let me just write it out. So let's say that we have neon gas that flows at 1 kilogram per second through an adiabatic reversible compressor. Okay. It enters at 100 kilopascal, 40 degrees C, and exits at 2 megapascal. How much power is required? Okay. Now, what if this problem were like the problem that I had attempted last week, I think it was last week, where we just used like water or the refrigerant 134A. If that was the case, we would have said, oh, well, that's an isentropic process. I would go into my property tables at the inlet at point 1. I would look up the entropy. And I would say, well, but isn't S1 equal to S2? I mean, adiabatic reversible, it's isentropic. There is no change in entropy. So once I found S1 and I noted that it equals to S2, then I would just go back into the property tables at the two properties that I know, which would be S2 and P2, and look up the enthalpies, and then just plug those into the first law equation and calculate the work. But remember, we're talking about gases now. So our first law equation is not going to be a function of enthalpies per se. It's really going to be a function of Cp times the temperature difference. I mean, that is the enthalpy change, but we have to find temperature data. Well, how do I get temperature data for an isentropic process? Can't I just use these relationships above? In this particular problem, I am given the pressure at the inlet and at the exit and the temperature at the inlet. So for an isentropic process, I simply use the equation in the box above, and I find T2, which is completely equivalent to me using property tables and saying S1 equals S2, and then at S2 P2 I can find T2. But now I've just done it through equations. Once I have T2, I plug it into my first law, and I solve for the work or the power. So let's just write that down. First, let me just set up the problem. Okay. So first things first, here's my compressor. I'm using neon gas. I'll just let 1 and 2 be inlet and exit. The mass flow rate is a kilogram per second. It's adiabatic and reversible, so heat transfer rate is 0. The fact that it's adiabatic and reversible means it's isentropic. We're given P1 of 100 kilopascal and T1 of 40 degrees C. And we're given P2 of 2 megapascal, and we're trying to find the power. Okay. So it's a pretty standard setup. All right, so what about the equations we're going to use? Well, it's the first law. It's a single stream steady flow process. Rate of heat transfer minus rate of work is the mass flow rate times the enthalpy change, and then plus the kinetic and potential energy changes. Now, I'm not going to bother to write out those equations because, quite frankly, we're just going to neglect kinetic and potential energy change. First of all, we don't have enough information to find that even if we wanted to, right? We do know the mass flow rate, but unless we knew the physical size of the inlet or the exit pipe, there's no way that we can find the velocity. So we just have to assume that there's no velocity change. We have no choice. And same thing with height change, right? We know nothing about the difference in height between the inlet and the exit. So we'll just assume that both of those are 0. We'll note, of course, that the heat transfer rate is also 0 because it's adiabatic, and therefore power is equal to, and I'm just going to move the minus sign over to the right-hand side. So W dot is equal to negative of M dot, and then this would be Cp times T2 minus T1. that would only apply, of course, if we have an ideal gas. An enthalpy change equals Cp times the temperature change. Now, we don't really know the average temperature for this process, do we? If we know the average temperature, then we can go into table A2 part B and at T average, find Cp at that average temperature. But what you'll find is that even if we wanted to do this, when you go into table A2 part B, it doesn't have any data for neon, right? Table A2 part B only has 6 gases, and neon is certainly not one of them. So it doesn't exist. So the fact that it does not exist means that we can't really use that. Why don't we just go into table A2 part A, and at room temperature, we'll find the value of Cp, which we'll just call CPO. And we just look up the number, and it's 1.0299 kilojoules per kilogram per Kelvin. We would always like to use the average temperature if we had it available to us. That's the most accurate, but we don't. So we'll make the approximation, and that's good enough. That's it. Problem's done. Back to the first law. Well, problem isn't totally done yet, is it? I don't have T2. Okay, so I back that up. Not totally done. What do? We somehow need to find our exit state. Well, it's an isentropic process, right? And for an ideal gas, we're going to use the equations above. So we'll use the one that's a function of temperature and pressure. So the one we're going to use is the one that says temperature ratio equals pressure ratio to the k minus 1 over k. This has to be solved first. Then we can solve the first law, right? All right, so let's just do this. T2 is my unknown. T1 is given to us as 40. Now keep in mind that we have to convert this into Kelvin. So that's actually 313.15 Kelvin, right? We just add 273.15 to 40. And then the pressure ratio, let's see, the exit pressure is 2,000 kilopascals. The inlet is 100. So you certainly need to make sure that your pressures are right. As long as you're in table A2 previously, we really should have looked up the value of K as well, right? We knew that we were going to need it eventually. K is the ratio of specific heats. That's the data that's in that final column, and it's 1.667. So we'll just use 1.667. So K minus 1 is 0.667 over 1.667. And we solve this, and we get the temperature of 1,038.3 Kelvin as the exit temperature. So this one little equation is how we deal with an isentropic process for an ideal gas. Now we go back up to our power equation from the top, our first law. And now we can finish it. So minus 1 kilogram per second, 1.0299 kilojoules per kilogram per Kelvin. I might as well just stick with temperatures in Kelvin, although we have seen in the past that temperature difference in Kelvin and Celsius are both the same, so we could use the temperature difference in Celsius, but I already have my numbers in Kelvin. I might as well just keep them. And we go through the mathematics. You can see we end up with kilojoules per second, which is the same thing as kilowatts. We get minus 746.8 kilojoules per second, or kilowatts. And the fact that it's a negative means that power is required, right? Of course it's required, right? The compressor is taking energy from a motor and transferring it to a fluid. It's causing the fluid to move. It's greatly increasing its pressure and temperature. So we would definitely expect a negative sign, and that's what we get. So are there any questions then on this example problem? Good. Okay. Well, the next topic, because we're now done with this, I don't have another example problem prepared. The next topic deals with what's called steady reversible work. This is the next chapter in your textbook. I think it's, section 7.10. I am not going to go through this section because basically when you finally get to the end of it all, what you find is that there's only one little piece of information that's of any use for us. So this section is called steady flow work, or sometimes called work for reversible steady flow processes. And this specifically applies to reversible processes. So again, this is in section 710 of your textbook. Now, I could certainly go through a derivation and let's see how much time we have. Yeah, I guess I can go through a quick derivation. If we have a single stream steady flow process, let's go back to one of those TDS relationships, the one that says TDS equals dH minus VdP. Okay. If we have this particular relationship, and we're specifically talking about a reversible process, we would also often be interested in adiabatic reversible processes. So from this, and let's assume that we have an adiabatic process as well, from adiabatic and reversible. In that case, then that means isentropic, right? And another name for isentropic is no entropy change, or just ds equals 0. So therefore, from the equation that's above, I would just note that dH has to equal VdP. Now, what if I integrate this over, let's say, a steady flow process from some inlet to some exit? So this equals H2 minus H1. This just equals the integral of VdP from 1 to 2. Now, if you think about it, isn't this enthalpy change just part of the first law equation for this type of process? So from the first law, again, we're dealing with a single stream steady flow process, and again, we've assumed that it's adiabatic and reversible. Then basically have Q minus W, and I'm just writing it on a per unit mass basis. This equals the enthalpy change, and then plus the kinetic and potential energy changes. Here now, we would just note that the enthalpy change is the integral of VdP from 1 to 2. I'll also note that since it's adiabatic, then the Q equals 0. So we basically end up with this form of the first law. And then I want to note that we're only going to be using this particular type of relationship for even a further special case, which is for liquid flow. So for a liquid that's undergoing an adiabatic reversible process, then what would be the integral of VdP? Let's keep in mind that for liquids, and we've talked about this before, they're fairly incompressible, right? In other words, the specific volume is essentially constant over a wide range of pressure increases. So I'll note that, but V is more or less constant, right? Incompressible fluid, just like you'll be studying in your 311 and 312 classes. And therefore, this integral of VdP, well, if V is constant, it's going to come out. We just have the integral of dP from 1 to 2, which basically means it's the specific volume times the pressure change. So we can now plug this back into the first law. So we plug this in above, and we get that negative of the work equals the specific volume times the pressure change. And again, plus kinetic and potential energy changes. Now, for many, many problems, we're just going to neglect the kinetic and potential energy changes. For some, we won't, but this is the basic equation, okay? Now, if we look at the absolute value, in other words, the work input, then this is just V times P2 minus P1. Now, I will note that V2 and V1 are the same. Usually, we're going to know thermodynamic state point 1, so usually I would just put a subscript 1 there, just to remind us that we want to find this data at point 1. But again, V1 is equal to V2. So this is the result. I guess I should include my kinetic and potential energy changes. So if we happen to have steady flow reversible work, if we happen to have a device that moves a liquid in an ideal fashion, then this would apply. Now, frankly, there's only one single device that does this, and that would be a pump, right? Turbines move vapors, two-phase mixtures. Compressors move vapors or two-phase mixtures. Some turbines might actually move liquid, like hydraulic turbines. But where this is going to be the most useful to us is for the analysis of pumps. So this basically applies to the ideal pump, you know, one that is both adiabatic and reversible, and therefore isentropic. Okay. So that's all we really need out of section 710. In fact, let me go through an example problem so that I can, just illustrate this. By the way, we don't have to use this. We could always just use enthalpy data from the various tables as necessary, but this just gives us a simplification or a shortcut, if you will, for solving problems that involve an ideal pump. All right, so with all this in mind, let me go through one more example problem, and that might be all I have time for today. We'll see. I might be able to move on. This will be problem 105 from chapter 7. So if we could have our computer switched on one of these screens. So this is 7-105. And this is from your 8th edition, the current edition of the book. All right. So basically it says that water enters a pump of a steam power plant as a saturated liquid at 200 kilopascal and at a rate of 45 kilograms per second and exits at 6 megapascals. It says neglecting changes in kinetic and potential energy, assuming the process to be reversible, then determine the power input to the pump. Okay. So this is the kind of problem that the above equation would specifically apply to, right? If we're trying to find the power for this type of reversible process, then we just have to use the mass flow rate times the work per unit mass, which is from the equation above. So here's my pump. Let's let, again, 1 and 2 represent the inlet and the exit. We're given that this is part of a steam power plant, so it's H2O. P1 is 20 kilopascals and is a saturated liquid. And the mass flow rate is 45 kilograms per second. And then the only exit property we know is the pressure, so P2 is 6 megapascals. It tells us we can neglect kinetic and potential energy changes. We'll assume they're both 0. We're told that it's reversible. And we're trying to find the power input. Now, we recognize that the power input is just the mass flow rate times the work per unit mass input. And because it's a liquid, right, it's using a saturated liquid from a pump, and it's a reversible process, then this is equal to the mass flow rate times the specific volume at that inlet times the pressure change. I mean, this is really easy, right? If we wanted to, we could go into our thermodynamic property tables at P1 for a saturated liquid. We could look up S1. We could say that S1 equals S2. If we had good compressed liquid tables, then at P2 and at S2, in fact, at 6 megapascals, that may be big enough to use table A7 for. But anyway, if we knew S2, which equals S1 and P2, we could then find H2. And we could have just simply used m dot times delta H. I mean, that would have been an acceptable way. But this is just a simplification, right? This makes it so that we have almost no information to look up. The only thing we really need to look up is the specific volume of the saturated liquid at that given inlet pressure. Once we've done that, it's just a matter of plugging numbers into the equation and we're done. So let's just do that. At P1, saturated liquid, it's water, it's SI units. We go into, we're going to table A5. And we get V1, which is equal to VF. And this is 0.001017 cubic meters per kilogram. And that's it. So then the power, we've got 45 kilograms per second as the mass flow rate, 0.001017 meters cubed per kilogram as the specific volume. And then we have our pressures. Let's just keep them in kilopascals. So we have 6,000 minus 20 kilopascals. And if we just go through a little bit of mathematics, we end up with 274 kilojoules per second, which is kilowatts. Now note that this is really magnitude, right? When this equation was developed above, we know that it was really the negative of the work equaled V times delta P. So this is a magnitude. We still understand that this is a work input requirement, and that's why I've put W dot in. By the way, you may wonder about the units. I think we've talked about that enough times. We know that a kilonewton per square meter is the same thing as a kilopascal, and we also know that a kilojoule is the same thing as a kilonewton meter, right? So basically that's how everything is going to cancel out, and it's going to leave you with just kilojoules per second. Yeah, meters cubed cancels, kilojoules per second, kilowatts, so no real unit issues here. So there's an example of how one uses this material regarding reversible steady flow work for a liquid. Now, quite frankly, you're not going to have many problems like this. I might give you one. This is really more useful at the beginning of ME302 when we're starting to look at actual steam power plant cycles. There's a cycle called the Rankine cycle that you're going to be looking at considerable depth in your 302 class, and you're definitely going to use this type of information for that. You may also use it for other problems, as we'll see here over the next couple of days. So, any questions then regarding this particular example problem? Okay. So yeah, it looks like I do have a little more time. So I'm just going to continue. We're still on track here. It says that we're supposed to start section 712 now, and that's what we're going to start talking about. Okay. Let me just pause for a second to see if there's any questions, because we are actually getting into some somewhat new material. But we are going to have to use a lot of the material that we've already learned as we get to this new material. So the new material is called isentropic efficiencies. So, isentropic efficiency of a steady flow device. Now, isentropic efficiencies, by the way, sometimes are called adiabatic efficiencies, but there's a lot of names for it. Oh, yeah, we don't need the example problem here anymore. Okay. So, first of all, we have to understand that when we talk about isentropic efficiencies, this has absolutely nothing to do with thermodynamic efficiencies. Okay? A thermodynamic efficiency or thermal efficiency is a relationship between the heat added and the work done. By the way, on your midterm that I just returned earlier, there were several students that used thermodynamic efficiencies to solve refrigeration cycle problems, which is completely incorrect, right? I mean, thermal efficiencies are only used for heat engines. Coefficient of performances are only used for refrigeration cycles. This topic on isentropic efficiency has nothing to do with any of those. We're talking about a different type of efficiency entirely. And this is the efficiency associated with the steady flow device. Now, we're specifically going to be talking about 3 different devices here. One is turbines, and the others are pumps and compressors. These are the 3 steady flow devices that we're going to be concerned with in this particular topic. And quite frankly, these are the 3 work devices that are going to be used in any real power plant cycle, right? We know that a real power plant, a real heat engine, if you will, a power plant is just a heat engine, there is going to be some power input, which is going to have to come from a pump or a compressor. There is going to be some power output, which is going to have to come from a turbine. And now what we need to do is we need to be able to analyze these in a little more detail than we've been able to analyze previously. Now, what do we mean by isentropic efficiency? What I'm really doing here is I'm doing nothing more than I'm going to compare the ideal work to the actual work. Okay. That's going to be my isentropic efficiency. And we understand that the actual amount of work is different than the ideal amount of work, right? If we have let's say a pump, we know that the maximum amount of work, or let me put it the other way, since a pump is an input device, we know that the minimum amount of work that would be required by any pump would be that associated with the ideal pump, right? If we have the ideal compressor, the minimum amount of work would be that associated with the ideal compressor. In other words, the isentropic compressor or the isentropic pump. The same thing goes for a turbine, although a turbine is a work output device. We know that nothing could provide more work output than the ideal turbine, that is the isentropic turbine operating between the same sets of conditions. So that gives us a feel for the need for isentropic efficiencies. There's really 2 isentropic efficiencies, one associated with the turbine and one associated with the pump or compressor. Please recall, as I mentioned this before, that a pump and compressor are just names for the same device. A pump moves a liquid, a compressor moves a 2-phase mixture or a vapor, but they're work input devices, right? They have rotating impellers, there's a motor attached, the motor provides a work input, putting rotation on the impeller, and then whatever fluid comes in gets sucked up in the impeller and gets pushed out at a higher pressure with a certain flow rate. That's what happens in a pump or a compressor. A turbine is exactly the opposite, right? But still, the definition of the isentropic efficiencies would be a little bit different. For a turbine, first of all, we're going to use eta for efficiency with the subscript T. So this is the isentropic efficiency of the turbine. And it's going to be defined as the actual work over the ideal work. Okay? Remember, nothing could produce more power than the ideal turbine. Nothing is going to be greater than the W term in the denominator. The actual amount of work output has to be a little bit less. The turbine isentropic efficiency, therefore, has to be less than 1, or if you will, less than 100%. So that's why we define it in this way. And this is an actual definition, so I really should put 3 lines on my equal sign. On the other hand, with regard to a pump or a compressor, first of all, I could just use eta with the subscript P for pump, C for compressor. But now we know that nothing will require less work input. And for our efficiency to be a number that's no greater than 100%, we have to define it in the opposite sense. We need to put the ideal work over the actual work. Okay. So the ideal work would represent the minimum possible work that could be required. The actual work is going to have to be a number greater than that, right? Because we're going to have to overcome the various frictional losses, fluid friction losses, rotational friction losses within the mechanical components of our pump, turbine, or compressor. So there's no way that the actual work is going to be the same as the ideal work, right? There's definitely going to be a difference. And that's why we define these isentropic efficiencies. Now again, these are definitions, So we really should put 3 lines in my equal sign so that we represent, or so that we recognize that. Now, another thing that I want to note further is that we're not going to want to write out the words W or work, actual and work ideal all the time. So I'm just going to use the subscript A for actual and the subscript S for ideal. So for the turbine, the isentropic efficiency is WA over WS. For the pump or compressor, it's WS over WA. Okay. Now, why do you suppose we use S? We know that S stands for entropy. What is the ideal work process? Isn't that the adiabatic reversible work process? Isn't that the process where there is no change in entropy? Which means using the subscript S makes sense to us, right? S reminds us that for the ideal case, there is no change in the entropy. And then one last thing to note here today. I could write this as a total quantity, that is total work, like I've done here. But I could also write these on a per unit mass basis, right? I can divide by mass, both in numerator and denominator, and I would get lowercase WA over lowercase WS, or in the case of the pump or compressor, lowercase WS over lowercase WA. And then further, I would note that I could do this on a per time basis, right? I could write this on a per unit time basis. In other words, I could divide by time in the numerator and denominator. So this could also be just W dot A over W dot S, or inverse for the compressor pump, W dot S over W dot A. So all of these are acceptable ways for us to write out the isentropic efficiency of these various devices. And let's note that these efficiencies, whether it's a pump, turbine, or compressor, they all have to be less than 1.0, or if you will, less than 100%. So this is what we're going to begin studying now. We're going to have to figure out what is really meant by isentropic efficiency. Well, I think we kind of understand now what it's useful for, but now we have to figure out how to use it for real problems. And just to give you kind of a heads up on that, what we're going to do when we solve for these pump, turbine, or compressor problems is first we're going to assume that they're isentropic and calculate the work as if they were ideal processes. And then we're going to apply the isentropic efficiency equation, having been given the isentropic efficiency of that device in order to get the actual work associated with the pump, turbine, or the compressor. So it's really not that complicated, but it certainly is a little bit confusing, and granted, this is new material. So that just gives you a little heads up as to what we're going to be covering here. I shall note that whenever you buy a pump, turbine, or compressor out in the commercial or industrial world, you're always given a curve that tells you exactly what the isentropic efficiency is for any known operating point for that particular piece of rotating equipment. So it's not like you're just going to be left hanging. Now, granted, if you go down to the Home Depot and buy some cheapo pump, turbine, compressor, whatever, they're not going to give you any information about that device. But if you're in the world of building steam power plants and you're buying a $200 million steam turbine, you want to know exactly how efficient that thing is. So that will always be given to you. So that's all we have for today. This will certainly be continued next time. Please don't forget to turn in the homework that's due today. If you didn't pick up your homework from last time, it's up here. The exams are up here from last time. Is there a question? I forgot to assign the homework for the week, but it's actually the homework for this week and for next week. So yeah, maybe before you leave, let me just put that down here. In fact, I'm just going to give you homework right through the end of the quarter. By the way, this homework you're turning in today is the last homework set I'm going to actually collect from you. You are responsible for still 2 more weeks worth of homework, but I'm not going to collect it. I'll actually post the solutions for all of it by next Monday, so you have at least a full week before your final exam. Anyway, this is homework set 8 from chapter 7. Let's see, 92, 106. Yes, set number 9, you're right. Homework 9. Anyway, 92, 106, 118, 119, 120. And then from chapter 9, which we're probably not going to really get to until next week, we have 83, 87, part B, and 91. By the way, for all 3 of these, you want to use constant specific heats. That applies to these 3 problems from Chapter 9, not necessarily the ones from Chapter 7, but the ones from Chapter 9. Yeah, so those 5 problems from Chapter 7, a few from Chapter 9. Anyway, I'm sorry I'm holding you a little bit late today. Anyway, here's your last homework set. Oh, yeah.